For Bohr, it's important to note that the formulas that I put in the notes are not actually on your formula sheet, which means if you are ever asked these questions on a diploma exam, it's not that you're going to have to memorize these formulas. What they would be is they would be provided within the question, or what would probably happen is there would be kind of a little scenario that would have you calculate three or four questions, and they would give you the formulas for that scenario. Do not think that you have to memorize these formulas. No formula in Physics 30 needs to be memorized. It's on your formula sheet. You may have to build formulas using multiple formulas on your sheet, but never memorize them. So for my exam, sure, build your own little formula sheet to help you if you need to. Keep your notes beside you if you want anyway. I'm not checking for a formula sheet, but for the diploma, just remember that what's on your formula sheet is all you need. If there's other formulas, it's provided within the context of the question. Realistically, on the diploma, the focus is more so on the theory rather than the calculations. But if you can do calculations, it will also help you understand the theory. So I like the fact that we are going to provide you some calculations, but understanding what the Bohr model is, how it's different than Rutherford, how Rutherford's model helped to create it, how Thomson's work has helped to create this, how Planck ties into this, all of that shows itself in the calculations of the Bohr model. And there's a couple formulas that you'll work with, and even in this first example, I'm going to do it two different ways to show you how Balmer would have used his formula to create this, or to do this question, where Bohr did this a different way and got the same result. And that was really significant because it's showing that even though they did these with completely different methods for hydrogen, they found that hydrogen was quantized, the energy levels are true for the hydrogen atom. So there's a lot of evidence that was supporting this. The last part of that unit was, okay, it worked for hydrogen, the formulas worked nicely for hydrogen, but it didn't work for anything else. So the last part of the notes was, okay, here's this Frank Hertz experiment that pumps electrons through mercury vapor, and even though the formulas don't work that were created for Balmer and Bohr, it still showed that they're quantized. And the formulas are significantly different for the next atom, not even mercury, but even if you went from hydrogen to helium, everything falls apart except for the concept that the electrons were contained within specific orbits. How you calculate it is completely different though. Okay, so the first example I'm going to do, I'm actually going to do it two ways. I'm going to show you method one, which is the probably the more efficient method, and then I'll show you how Bohr would have done this. So method one, I'm going to show you how Balmer or Rydberg would have used this formula to actually calculate the wavelength. So because it's a hydrogen atom and it's going from energy level 7 to energy level 4, I always just say, okay, the lower level is energy level 4, the upper level is energy level 7. Rydberg's constant, which would be given to you, is 1.10 times 10 to the 7, 1 over meters. And what you're doing is you're looking for wavelength. Well, this formula is quite easy to work with. 1 over lambda equals RH times 1 over the upper orbital squared minus 1 over the, lower orbital squared by the upper orbital squared. It wouldn't matter, you'd get the same result. One is just going to be negative. The key is wavelengths are always a positive number anyway. So if you punch this in, 1 over lambda equals 1.10 times 10 to the 7, 1 over meters. times 1 over 4 squared minus 1 over 7 squared. Punch this in and then take this reciprocal. So I'll kind of describe it to you here. So I'm going to work out the square brackets first. I'm going to go 1 divided by 16, subtract 1 divided by 49, which is just the square of those numbers, times by 1.10 to the exponent 7. That's equal to 1 over lambda. So if you use your x to the negative 1 key or your reciprocal key, you should get 2.16 times 10 to the negative 6 meters. And if you remember some of the stuff I was talking about Bohr, we know that the Lyman transitions were to orbit 1, and that was ultraviolet. The Balmer transitions were to orbit 2, and that was the visible region. Anything after Balmer would give you a infrared type wavelength, infrared type frequency. So if we're transitioning to level 4, then we should see less energy from 4 to 7, because the energy levels are closer together. So we get a wavelength of times 10 to the negative 6, which is in the ultraviolet region. So that, or not ultraviolet, sorry, the infrared region. So it should make sense when you calculate these that you should get a reasonable number. You shouldn't see X-rays coming from this. The electron transitions that we talked about way back when, electron transitions gave you infrared, visible, and UV light. No X-rays, no radio waves, no gamma rays. This is not enough energy. Only a transition to level 1 gives you UV. Transition to level 2 only gives you visible. Transition to levels 3, 4, 5, 6, and 7, and so on, always gives you the infrared region. So this is the easier way to do this. If you're given the upper and lower levels, I strongly suggest using this formula. It's a little bit quicker to work with. It's hard to manipulate for upper or lower value, but it is something you can do. We've worked with the focal length formula. This is a very similar setup to a focal length formula, so you can manipulate it. You have manipulated that one. You could manipulate this one. Here's how Bohr would have done this. So I'm going to do this again. I'll show you that we can get the same result with a different method. So method number 2, Bohr would have used these energy formulas. Bohr came up with this energy level formula, and we know that we have, if I can go back to my question, I have a n value of 4 and an n value of 7. So I have n equals 4, n equals 7. What Bohr would have done is he would have used this energy formula, which I'm going to put up the top here. Energy at some level is going to equal to E1 divided by n squared. And Bohr would have calculated what E4 was. E1 off your data sheet, or sorry, not off your data sheet, but off the out of the notes, E1 is equal to, and I'm going to leave this in electron volts for now, negative 13.6 electron volts. So I'm going to go negative 13.6 electron volts divided by 4 squared. Bohr would have worked out how much energy the electron would have at these levels. So if you go negative 13.6 divided by 16, in energy level 4, the electron would have 0.85 electron volts. Be careful. In your notes it says energy levels are always negative, but the energy of the electron is the same value but positive. The electron's energy isn't negative. The electron's energy is positive. It's the level we classify. Why do we classify it as negative? is because if the electron was sitting in that fourth orbit, I would need 0.85 electron volts of energy to ionize it, to make it an ion. Bohr would then calculate what E7 is, negative 13.6 electron volts divided by 7 squared, and he would have E7 equal to negative 0.278 electron volts. And then what he would do is he would calculate the energy of the transition. So if he was going to calculate the energy, he would use the other formula I showed you, E upper minus E lower, and he would find out how much energy was given off or absorbed in going from level 4 to 7 or 7 to 4, depending how your question was worded. So if we go negative 0.278, subtract negative 0.85, the energy that was part of the transition gives you 0. And I kept my exact values in here, 572 electron volts. Then Bohr would go to Planck's formula and say that energy equals to hc over lambda. So lambda equals hc over energy. And you can see it's a lot more complicated in this method, but it still will give us, and I'm going to prove to you, it will give us the same value. So I'm going to use Planck's constant in terms of electron volts. Off my data sheet, it is 4.14 times 10 to the negative 15 electron volt seconds times 3 times 10 to the 8 meters per second divided by the energy 0.572 electron volts. And if I punch that in, hopefully I get the same value. Otherwise, I've done something wrong. And I do get 2.17 times 10 to the negative 6 meters. It's more of a rounding error than anything else in my question. Remember, times 10 to the negative 6 is 0.0000217, and we're comparing it to 0.0000216. A very insignificant difference between those two values. So the neat thing was, these guys did this completely independent of each other. Balmer just kind of played around with the pattern of numbers and came up with that formula in method 1. Bohr, after working with Rutherford and Thomson and understanding what Planck was getting to with energy being quantized, put it all together. Bohr was an amazing mathematician, and he was able to take everybody's work and use it to explain something else. He didn't do anything in terms of an experiment to do this. He put everybody else's work together. He was the one that unified it all, which was really amazing.